Now we're going to look at molecular vibrations on a specific example, and we're going to spend a lot of time exploring carbon monoxide because it's a nice system. So let's look at this here. We've got a carbon with mass 12, an oxygen with mass 16 in atomic units. There's a nice stiff bond there, a triple bond, and it's about 1.2 angstroms in length. So that's basically our setup here. So the reduced mass of this system is 12 times 16 divided by 12 plus 16, which is 28, and that comes to about 6.86 atomic mass units. That's the first thing we do when we look at the system. Notice that's just a little bit less than a half of the average mass. So that's a pretty good way to begin to, if you say that that the average mass is let's say 14, which it is, divide that by 2, you get 7. The reduced mass is just a scooch smaller than that because of the asymmetry. The 12 outweighs the 16 by a little bit. So when you have similar masses, the half the average and down a little bit is a pretty good guess at what the reduced mass is going to be. So you can tell right away that that's basically the right number. We didn't make a terrible math error. One last time for the MKS units. That reduced mass is 1.1 by 10 to the minus 26 kilograms. The spring constant of that bond happens to be 1,850 newtons per meter. That's a ridiculous number to use for a bond, but it is the MKS value. Just to give you a sense, so a kilogram is about 10 newtons in one gravity. So if you held up a 180 kilogram weight, that's how hard a single carbon monoxide bond would pull back at you if you somehow managed to stretch that bond by 1 meter. If you pulled those springs back by 1 meter, they'd be pulling it. It would be like holding up a 180 kilogram person, which is pretty hard to do. Okay, so the strength of the bonds of chemical bonds is really enormous. Of course, you can't pull a bond back a meter. You can't even pull it an angstrom, as we'll see. So the units are kind of crazy, but just to give you a sense of exactly how formidable the strength of these bonds is, that's a kind of nice number. So the spring constant divided by the reduced mass, 1.7 by 10 to the 29 per second, because that reduced mass is really, really small, so you flip it over and you get a really, really big number per second squared, excuse me. We take the square root of that, and we get 4.1 by 10 to the 14 per second, which are hertz in the units. So 4.7 by 10 to the 14 hertz. So the frequency is 1 over 2 pi times that square root, and that comes to 6.5 by 10 to the 13 hertz, and that is 65 trillion hertz. A trillion is 10 to the 12. So we call that 65 terahertz. So molecular bonds have characteristic frequencies in the tens of terahertz, typically. So that's a pretty useful. You'll hear spectroscopists talking about those units a lot. So 10 trillion or more cycles per second is a typical frequency of a vibration. It's actually rather important to know. So 65 terahertz here for carbon monoxide. Turn it into wave numbers by dividing by the speed of light, and we get 2,170 wave numbers. Again, incredibly important characteristic to know that especially stretching vibrations of if we have a reasonable reduced mass tend to be in the 1,000 and give or take 1,000 wave numbers. The region in FTIR between a little less than 1,000 and a couple of thousand is called the fingerprint region, because the exact frequency of the vibrations is very, 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 very characteristic of the reduced mass and, in other words, the molecules making up the bond and the bond strength, that curvature itself. The bond strength doesn't change incredibly much from molecule to molecule, though CO has a relatively stiff one because of the triple bond. But of course the reduced mass does. And so that exact frequency becomes a very, very characteristic property of a given vibration, of a given bond, and we can thus identify molecules based on it. Now let's flip this over and use the units we like. These are AMU angstrom inverse centimeter units. So we're going to use atomic mass units for mass, angstroms for length, and then inverse centimeters or wave numbers as our energy. We're going to take joules and divide it by HC, and that's going to give us the wave number equivalent energy units. So our characteristic frequency over the speed of light by the formula from last time is 1 over 2 pi c times the square root of the k over mu that we just worked out in MKS units. But if you convert that into atomic units, well, first thing we have to remember is that it's 1 over 2 pi c times the square root of the second derivative of the potential divided by the reduced mass. And we'll figure out those second derivatives. This turns out to be 5.8074 times the square root of the second derivative of the potential divided by the reduced mass. If the potential is given in inverse centimeter angstrom units, so the length is, we have a second derivative, how much the y value changes in x. The y value, the energy, will be wave numbers, inverse centimeters. The x values will be angstroms, and the energy units are going to be wave numbers, and the masses are going to be atomic mass units. So if we use the molecular units, the formula for the characteristic frequency of the vibration in wave numbers becomes 5.8074 times the square root of the second derivative of the potential divided by the reduced mass, about 5.8. A good number. You should certainly write that down on your sheets. So that one, V double prime, the units are 1 over centimeter angstrom squared, and the reduced mass has to be in atomic mass units. For carbon monoxide, the second derivative of the potential in these units is about 9.4 times 10 to the fifth 1 over centimeter angstrom squared. So that's a fairly large number. That's 937,000 1 over centimeter angstrom squared. But we take a square root of that, and also an angstrom even is a long way for a bond to stretch, as we'll see. So that's why that reduces to a smaller number with vibrations. So this is 5.8074 times the, so we got 9.369 times 10 to the fifth, and we divide by the reduced mass, which is now 6.86 AMU, and that comes to 2,146 inverse centimeters. Not quite the same because I rounded some numbers, so I missed. We got 2150 basically from this formula. We got 2170 above. That's just rounding. Obviously, the exact number is exactly where it is, but as we push some numbers around, the numbers that are picked for the example don't come out exactly the same. But basically, we use the atomic units. We get we can keep track of things in numbers that are carrying around 1.1 by 10 to the minus 26 kilograms is hard. Thinking of 6.9 atomic mass units is not. Remembering 5.8 even is not very hard. The force constant you still got to work out, but it's in sensible units. It's really, 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 really important to get a sense of scale for these different motions of molecules. It's really one of my main objectives for this course, and it's one of the reasons that we use these atomic units, because it's possible to file away characteristic numbers. So we've already looked at rotation, and we've seen that the B value for rotation, the rotation constant, in atomic mass units numbers goes like 16.86 divided by the moment of inertia, where the moment of inertia is AMU angstrom squared, and the B value is going to come out in wave numbers. And for most molecules, that's of order 10 centimeters is actually a large B value. As the moment of inertia grows, it goes down to 1, and even significantly less than 1 wave number. So rotations, molecular rotations, have characteristic values, and thus characteristic energy scales, that are in the neighborhood of a wave number, 10 wave numbers max. Now we've just seen that vibrations, however, have characteristic frequencies given by 5.8 times the square root of the second derivative of the potential divided by the reduced mass that come out more like 1,000 wave numbers or even more. 2,000. CH stretches, as we'll see, are more like 3,000 wave numbers characteristic. An OH stretch is 3,600 wave number characteristic. So thousands of wave numbers. There's 100 times more energy characteristic in a molecular vibration than in a molecular rotation, and this really matters. So it takes so much more energy to make a molecule vibrate. And one of the things about quantum mechanics is so per unit that we stick into the system, we are only able to stimulate the system quantum by quantum. So we have to add a quantum of energy because the energy levels, the states, are quantized. So they're only specific energies, and the separation of these energy levels for vibrations is of order 1,000 wave numbers, as opposed to the rotation, which have states that are much, much more closely separated. And that really matters in the way they behave. Another thing that we'll get to a little bit more later is that the characteristic energy at a certain temperature, if it's given by the Boltzmann constant, Kb times the temperature, and then we're turning everything into wave numbers, so we always divide by Planck's constant times the speed of light. So there's this wonderful term of Kb times T divided by Planck's constant times C. It's got all these fundamental constants in it multiplied by the temperature. It's like RT over Hc as well, if you like to think about the gas constant and do it in molar units. Those are the same thing. But however, if you plug it in, at 300 degrees Kelvin, a characteristic energy in wave numbers is about 200. And again, that's a really important thing to know. So what this is telling us is that at 300 degrees Kelvin, there's more than enough characteristic energy floating around to excite rotations, because we've got a bath that's got 200 odd wave numbers of energy sort of for the taking in all sorts of modes of motion, and that means that a molecule can essentially borrow on that bank and easily change its rotational energy levels. But it isn't easy to do that for vibrations. So rotations are active at 300 degrees Kelvin. Molecules are rotating quite freely, but the vibrations aren't, because that characteristic 200 wave numbers is much less than characteristic vibrational energies, and the vibrations are kind of frozen out. So many molecular vibrations, except the loosest, floppiest, backbone bending kind of almost internal rotation modes, all of the kind of classic stretching vibrations of molecules are really inactive at 300 degrees. And you'll see much more of that in next term when you cover statistical mechanics and thermodynamics. But this is really the basis for understanding why some modes of motion are active, rotations specifically, and obviously translations, molecules move around, but others are quite frozen out, and it depends very much on actually the temperature that the system has. Even though the vibrations are frozen, there's another little fun quantum thing going on here, which is that the consequence of the characteristic energy for a vibration being 1,000 or so wave numbers, and there are only 200 wave numbers kind of available at 300 degrees Kelvin, is that the vibrations will almost always tend to be in the vibrational ground state at 300 Kelvin. So the system's sitting in the ground state, but it doesn't mean that it's sitting still because of this sort of quantum ADD that confined objects have in quantum mechanics. There's a thing called zero-point displacement. Remember that the sigma squared, the characteristic width squared of the Gaussian, is given by our favorite constant, 5.8074, divided by the square root of the second derivative of the potential energy times the reduced mass. Slightly different formula, because now we're looking for the width, the characteristic width of that normal distribution. For carbon monoxide, sigma squared thus is 5.8074 divided by the square root of 9.37 by 10 to the fifth times 6.86. So that comes to 0.0022 angstroms squared, but we have to take the square root of that, so the width is 0.05 angstroms, about. So 5/100ths of an angstrom, and for a normal distribution, sigma is actually the half width. It's like the half width as you go down the Gaussian function. So actually, if we're going to take the full width to this Gaussian function, where the bond length, remember, is about 1.2 angstroms. So here's the ground state. It's about 1085 wave numbers up, the 0-point energy of carbon monoxide. That's half of the characteristic frequency of a carbon monoxide vibration. So the 0-point energy is always half of that characteristic frequency. The full width from classical turning point to classical turning point, because that's where the inflection is about 0.05 angstrom on one side, about 0.05 angstrom on the other side. And so that full width is actually about 1/10 of an angstrom. It's about 10% of the full length of the bond. So that's how much the quantum system is kind of jittery, it's fuzzy. You can't say that the bond is exactly 1.2 angstroms wide. It's not. It's basically sloshing back and forth by about 10% of its full width. So about 1/10 of an angstrom or so comes out of that. And now for the carbon monoxide, it's actually pretty heavy. If we get to things like the 0-point displacement for our favorite proton, hydrogen, that can be quite large. Okay, it's not enormously large. It goes like the square root of the reduced mass. But we're up at 7, and hydrogen's down at 1. And so you can get, if you have 1/10 of an angstrom for heavy molecules, we can get up of order 3/10 of an angstrom or so for hydrogens. So hydrogens are actually quite, they're shifty. They're a little hard to find when it comes to exactly where they are. They're really beginning to have significant quantum behavior, and the fuzziness of their exact location is an interesting consequence of the quantization of the system.